Welcome to an exploration of one of nature's most fascinating chemical oscillators, the Belousov Zhabotinsky reaction, confined in microdroplets. The BZ reaction creates stunning, oscillating patterns that we can confine and study in tiny droplets and capsules. Let's start by understanding what makes the Belousov Zhabotinsky reaction so special. The BZ reaction is a rare example of an oscillating chemical reaction, first discovered by Boris Belousov in 1951. It displays beautiful periodic color changes, oscillating between red and blue states over time. The reaction cycles through oxidized red states and reduced blue states in a predictable periodic manner. The key chemical species include malonic acid, bromate ions, and a metal catalyst like cerium or ferroin. The overall reaction converts malonic acid and bromate to bromide, carbon dioxide, and water, but the mechanism involves complex oscillatory steps. To understand the BZ reaction mathematically, we use the oreganator model. The oreganator is a simplified kinetic model that captures the essence of the BZ reaction using three key chemical variables. The first equation describes the rate of change of species X, which represents the bromous acid concentration. The second equation gives the rate of change of Y, representing bromide ion concentration with a feedback term. The third equation describes Z, the oxidized catalyst, which oscillates between oxidation states. These coupled nonlinear differential equations produce limit cycle oscillations, meaning the system returns to a periodic orbit. Now, why would we want to confine this reaction in tiny droplets? Here's a key question. What happens to an oscillating chemical reaction when we shrink the volume down to micrometers? As we move from bulk reactions to mesoscale and microscale, the physics changes dramatically. The answer is that confinement introduces new physics, including stochastic effects, molecule number fluctuations, and altered diffusion. This has applications in microreactors, creating cell-like compartments, and achieving precise spatiotemporal control of chemistry. Let's examine the most important length scale in confined BZ reactions. The reaction diffusion length lambda equals the square root of the diffusion coefficient d divided by the oscillation frequency omega. This critical length scale determines whether oscillations can occur at all in a confined space. For typical BZ reactions, the diffusion coefficient d is approximately 10 to the minus 9 meters squared per second. The oscillation period T ranges from about 50 to 200 seconds depending on concentrations. Therefore, the angular frequency omega equals 2 pi over T, giving approximately 0.03 to 0.1 per second. Plugging in these values, lambda is approximately 140 micrometers, a critical number we'll use repeatedly. This 140 micrometer scale represents a critical boundary between different dynamical regimes. The droplet diameter compared to lambda creates three distinct regimes. In the first regime, when the droplet diameter is much greater than lambda, we see bulk-like behavior. Mathematically, when d is much greater than lambda, we get bulk-like oscillations with wave patterns. A droplet of 500 micrometers shows beautiful concentric wave patterns propagating inward. In the second regime, when the diameter is comparable to lambda, fascinating competition occurs. When d is approximately lambda, oscillations are modified with altered frequency and amplitude. At 140 micrometers, droplets show synchronized bulk oscillations without complex wave patterns. In the third regime, when droplets are much smaller than lambda, oscillations may cease entirely. When d is much less than lambda, oscillations can be completely suppressed or become irregular. A 20 micrometer droplet is too small to support sustained oscillations due to confinement effects. Let's calculate some concrete numerical examples for real experimental systems. Consider a typical water and oil emulsion where BZ reactants are in aqueous droplets. Suppose we create droplets with a diameter of 50 micrometers. The ratio of droplet size to reaction diffusion length is 50 over 140, approximately 0.36. Our prediction is that oscillations will be strongly suppressed or become irregular and stochastic. If oscillations occur, we expect the period to increase by 1.5 to 3 times the bulk value. Now consider larger microcapsules used in some experiments. These capsules have a diameter of 300 micrometers. The ratio is now 300 over 140, approximately 2.1. We predict clear oscillations with visible wave patterns forming inside the capsule. Approximately 2 to 3 wavelengths can fit across the diameter, creating target patterns. In small droplets, discrete molecule numbers become critically important. Here's an important question. How many molecules of each species are actually in a small droplet? Let's consider a very small droplet with a diameter of 10 micrometers. The volume is 4/3 pi r cubed, which equals approximately 5 times 10 to the minus 16 cubic meters, or 500 femtoliters. Typical BZ reactant concentrations are around 0.1 molar. The number of molecules N equals concentration times volume times Avogadro's number. This gives approximately 30 million molecules, which sounds like a lot. However, for minor intermediate species like bromous acid, there may be only thousands of molecules. The answer to our question is that stochastic fluctuations become significant with such small numbers. In tiny volumes, we must think of discrete molecules rather than continuous concentrations. Stochastic effects lead to fascinating new behaviors in confined BZ reactions. Different droplets of the same size show irregular oscillation periods due to molecular noise. Even if they start synchronized, droplets gradually fall out of sync due to stochastic phase diffusion. The variance in period squared scales as 2 kBt over gamma n times t, where n is molecule number. Over time, identical droplets develop different phases, creating a dispersion pattern. In extreme cases, some droplets may undergo oscillation death and stop oscillating entirely. Microcapsules and microdroplets behave differently due to their structure. A microdroplet consists of BZ solution completely surrounded by an immiscible oil phase. In droplets, reactants are fully contained but can exchange with the oil phase. A microcapsule has a polymer or lipid membrane shell surrounding the BZ solution. The membrane provides a physical barrier with selective permeability. The key difference is that the membrane controls mass transfer, affecting reactant replenishment. Microcapsules can often sustain oscillations longer because the membrane prevents reactant loss. Let's discuss how to design experiments with confined BZ reactions. The first experiment examines how oscillation frequency depends on droplet size. Create monodispersed droplets with diameters of 20, 50, 100, 200, and 500 micrometers. Measure the oscillation period for each size using time-lapse microscopy. The expected result is that period increases as diameter decreases below the critical length lambda. A graph showing period increasing as size decreases, particularly below the critical diameter. The second experiment investigates stochastic synchronization in droplet arrays. Create a two-dimensional array of identical small droplets in contact with each other. Start with synchronized initial conditions so all droplets begin oscillating in phase. Observe how the phases of different droplets gradually spread out due to stochastic effects. Measure the phase coherence time as a function of droplet size to quantify the effect. The third experiment explores chemical coupling between nearby droplets. Place droplets very close together with spacing less than 10 micrometers. Allow diffusive coupling of intermediates, like bromous acid, through the oil phase. The expected outcome is that synchronization depends on the coupling strength and droplet spacing. Two droplets exchange chemical signals, potentially synchronizing their oscillations. An important dimensionless parameter for confined reactions is the Damkohler number. The Damkohler number equals reaction rate over diffusion rate, or KL squared over D. For BZ reactions in droplets, L is the droplet radius, making this parameter size-dependent. When dA is high, the system is reaction limited, with uniform concentration throughout the droplet. When dA is low, the system is diffusion limited and concentration gradients form. For a 100 micrometer droplet, dA is approximately 125, indicating rapid mixing and uniform behavior. This high Damkohler number explains why smaller droplets behave as well-mixed batch reactors. Let's summarize the expected outcomes for different experimental conditions. Large droplets greater than 300 micrometers show bulk-like behavior with beautiful wave patterns. Medium droplets around 100 to 200 micrometers display synchronized whole droplet oscillations. Small droplets below 50 micrometers show irregular or completely suppressed oscillations. Three distinct regimes emerge based on the ratio of droplet size to reaction diffusion length. Membrane-enclosed capsules maintain oscillations longer due to reduced reactant loss. Stochastic effects become increasingly important as volume decreases below femtoliters. Let's work through a complete numerical example from start to finish. Suppose we want to design droplets that complete exactly 5 oscillations before the reaction stops. The bulk BZ oscillation period is 60 seconds in our formulation. In bulk, the reaction sustains for 30 minutes or 1,800 seconds before reactants deplete. Our desired lifetime is 5 times 60 equals 300 seconds. We need to choose a droplet size that accelerates reactant depletion by a factor of 6. The surface-to-volume ratio is the key parameter controlling reactant loss rate. Surface-to-volume ratio equals 3 over R, so it increases as droplets get smaller. To achieve 6 times faster depletion through surface loss, use droplets with approximately 50 micrometer radius. Therefore, a diameter of 100 micrometers should give us the desired 5 oscillation lifetime. But we must check if oscillations are even sustained at this size. The ratio of diameter to lambda is 100 over 140, approximately 0.71. This is a marginal case, where oscillations may occur, but could be irregular or have modified period. A better choice would be 200 micrometer diameter to ensure robust oscillations. In some cases, confinement can lead to Turing-type spatial patterns. Turing patterns arise when reaction and diffusion interact to create spontaneous spatial structures. The condition requires vastly different diffusion coefficients for activator and inhibitor species. In confined BZ systems, Turing patterns are difficult but possible with modified chemistry. A hexagonal spot pattern could emerge in larger confined droplets under specific conditions. The key is that confinement imposes boundary conditions that select specific pattern wavelengths. These confined BZ systems have several practical applications. One application is microfluidic chemical computing, where droplets act as oscillatory logic gates. Another is creating artificial cell prototypes that display autonomous oscillatory behavior. A third application is achieving spatiotemporal control in drug delivery systems. Arrays of communicating droplets can perform distributed chemical computation. Chemical sensors can be built that detect analytes through changes in oscillation frequency. Let's conclude with the key takeaways from confined BZ reactions. The critical reaction diffusion length scale lambda is approximately 140 micrometers for typical BZ conditions. 3 distinct regimes emerge: large droplets with waves, medium with bulk oscillations, and small with suppression. Stochastic effects from discrete molecule numbers become important below 50 micrometer diameter. Encapsulating membranes can extend oscillation lifetime significantly by preventing reactant loss. The surface-to-volume ratio is the key parameter controlling how quickly reactants deplete. These key parameters define the physics and chemistry of confined BZ reactions. Successful experiments require carefully considering all relevant length scales and timescales. Remarkably rich dynamics emerge from the simple act of confining an oscillating reaction. This field opens exciting possibilities for chemical engineering and synthetic biology applications.